Okay, we're going to start chapter 3. This is about the only easy day we're going to have in the whole chapter. So, enjoy it. So we're going to do 3-1 day 1. The whole chapter's on probability. Like I said, starts out kind of easy and then gets challenging. So first of all, we'll start with our definition of probability. Remember, a probability is just a number that gives the chance of an event happening. That indicates the chance of an event happening. And if you remember our probability scale, goes from 0% chance of something happening all the way to 100% chance of something happening. So nothing below 0%, nothing above 100%. Okay, and remember, probabilities can be given as percent, decimals, and fractions. So, and then right in the middle, equal chance of happening or not happening, we got 50%. But like I said, we can go decimals and fractions, so you could have a 1/2 probability or a 0.5 probability. Down here we've got 0 as a fraction and 0 as the decimal, and then 1 and 1. So again, this is absolutely does not happen. And this one's a guarantee, definitely will happen. So the higher a probability, the higher chance of something happening. Okay, lots of vocabulary to get out of the way. First one is outcome. Outcome is the result of a single trial of a probability experiment. All right, after that we've got sample space. Your sample space is all possible outcomes. So it's the list of all possible outcomes. And then event is to look for one or more outcomes when we get into probability, we'll be looking at the probability of an event happening. So it's looking for one or more of the possible outcomes as your event. So very simple. I'm going to give you an experiment, and you're going to list the sample space. I think I'll start a new page, though. Okay, example 1. I'll give you the experiment. And you will list out the sample space. So first we'll start easy. Roll a single 6-sided die. So your sample space, what could possibly turn up when you roll a die, is 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, or the 6 dots. So there are 6 total outcomes in that sample space. And there's a list of them. Flipping a coin. heads or tails. So you have 2 outcomes in your sample space. And then the last one we're going to talk about is picking a card from a regular deck of cards. Now, if you're not familiar with a deck of cards, you're going to want to make yourself familiar. I'm going to summarize it pretty quick here, but a lot of the questions are going to come from using a deck of cards, so you have to be familiar with that. So, a deck has ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then they have jacks, queens, and kings. So that's a total of 13 cards. And they have those in 2 different colors and 4 different suits. So actually I'm going to write that off to the side. So we've got ace, 2 through 10, jack, queen, king. We can have that in hearts. We can have the same thing in diamonds. The same cards are in spades, which is the upside down heart, a little tail. And then we have those same 13 cards in clubs. Okay. These 2 are both red, the hearts and the diamonds. The spades and clubs are black. So half the deck is black, half the deck is red. There are 13 of each suit, so there are a total of 52 cards. So I didn't want to list quite all of them, but 13 of each. Now, we want to talk about multiple part experiments. This is where it gets a little more challenging. So a multiple part experiment. What's going to help you see the sample space is to draw a tree diagram. Because a multiple part experiment means you've got more than one thing happening. So we're going to draw a tree diagram to physically see the sample space. So our second example, we're going to do a multiple part experiment. Okay, the first part of your experiment is to give a survey to some randomly selected people. And on your survey, the person is either going to answer, I agree with your statement, I disagree with your statement, or I have no opinion. Opinion. Okay, after they answer the question, then they're going to flip a coin. So I want you to be able to draw a tree diagram that will show me the entire sample space. And if you were here, I'd ask you how many outcomes do you think are in this sample space? Don't know if you know or not, but we're going to find out. Okay, so when you draw a tree diagram, you always start with a dot. Everything grows from that dot. So you do the first part of your experiment. You have 3 possible outcomes, so you need 3 branches to start with. The person could agree, disagree, or have no opinion. Then off of each one of those results, you do the second part of your experiment. So if you picked agree, you still have to flip a coin. So you could flip a head or a tail. If you disagreed, you still get to flip the coin. You could flip a head or a tail. And then if you pick no opinion, you still flip the coin. You can flip head or tail. Now the way to read a tree diagram is to follow the branches out. This top ending represents someone who agreed and flipped a head. There's one outcome. This is agree, flip a tail. There's our second outcome. Disagree, flip a head. Disagree, flip a tail. No opinion, flip a head. And then no opinion, flip the tail. Now you can physically see there are 6 outcomes in this sample space. Let's try another multiple part experiment. This one is having 3 children and looking at the different gender sequences. So example 3 is to have a family of 3 kids. So having a kid is an experiment, part 1. Have your second child is the second part of the experiment, and have the third child. So this is a 3-part experiment. And my question is, how many gender sequences are there going to be in the sample space? We'll make a tree diagram to show. Most people will say 6. 3 kids, 2 choices for each one, 6. Well, that's not quite right. Again, start the tree with a dot. Perform your first part of your experiment, have a child. How many outcomes are there? Well, you are either going to have a boy or a girl. Okay? So now we have the second part of the experiment, which is have another child. So if I had a boy first, I still have a second child. I could have a boy or a girl. Or if I had a girl first, I still have my second child. Boy, girl. So right now, if I wanted the gender sequences for having 2 kids, there would be 4 outcomes. Boy, 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 girl, girl, boy, girl, girl. 4 outcomes. But I got to have a third child, so off of each one of these, boy, girl, boy, girl, boy, girl, and boy, girl. Oh, pen's dying. So this end of this first branch represents my first outcome in my sample space, and that is having 3 boys in a row. This one's boy, boy, then a girl. Boy, girl, boy, just following the branches. Boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy. And girl, girl, girl. And if you count, 1, 2, 3, 4, 5, 6, 7, there are 8 outcomes in terms of gender sequence for having 3 kids. All right, a simple event. Another definition. A simple event will have only one outcome, or has only one outcome. So, what am I talking about? It'll become clear in my example. So we're going to roll a die, regular 6-sided die. And I'm going to name some events that I could possibly ask probability questions for. And all I want to be able to do is tell me, is the event I name simple or not? So, is the event simple? So the event we're first going to look at on rolling a die is roll a number less than 2. Okay, so you got to ask yourself, think about rolling a die. The sample space is 1, 2, 3, 4, 5, and 6. Well, how many numbers on the die are less than 2? Well, looks like there's only one, just the number 1. So this is a simple event. So I'm answering yes to simple. This time the event is looking at rolling an odd number. I'll put the 1. Rolling an odd number, well, if you look at the sample space, how many numbers are odd? Well, you got 1, 3, and 5. That's 3 outcomes, so this is not simple. It can only have 1 outcome to be considered simple. This one has 3 if I'm looking at odd. And then how about this? What about rolling a prime number? Go back. Do you remember what primes are? Primes are numbers that have to have 2 distinct factors, 1 and itself. So 1 is not considered prime because that only has 1 factor, just the number 1. 2 is prime because it only has 1 and 2 as factors. 3 is prime. That's enough for me to stop right now and say this is not simple. But let's see if there's any more primes. 4 is not prime, 5 is, and 6 is not. So there's 3 outcomes there, so not simple. All right, and then when we do our probability, we're going to be talking about 3 different types of probability. First one is theoretical or classical probability. And you're used to doing this kind of probability. We use this when each outcome is equally likely and the sample space is easily counted. So, when we do theoretical probability, the probability of some event happening, your bottom number is always how many outcomes are in the sample space. So it's the total number in the sample space and then your top number is the number of outcomes that match your event. So the number of outcomes that match the event that you listed over here. So it just starts out as a fraction. Okay, another kind of probability that we're going to be using, and we saw on the SAT when they gave us all those tables of information, all broken up, that's experimental or empirical probability. So it's based off of gathered data. So empirical also known as experimental, These are based on observations or some kind of gathered data. Or an experiment's repeated. So the probability of an event here the top number, again, the number of outcomes that match the event. Divided by, and your bottom number is, well, how many people did they talk to? How many observations did they make? What's the gathered data say? What's the total number of times you did an experiment? So this bottom number was generated by somebody gathering some data. So it's the number of times the experiment was repeated. And then our third one is subjective probability. And these are just our educated guesses. All right. So we'll go through some theoretical probabilities. Let's see, what number am I on? 5. I think. Skip something. 1 second. Oh, I skipped that one. Oh, that's all right. Okay, number 5. We're going to be picking one card from a deck of cards. So, because I know the sample space, and I'm not basing this off of what somebody did 100 times, this is theoretical probability. I know that there are 52 outcomes in the sample space when I pick from a regular deck of cards. There's 52 different cards I can choose out of that deck. So, their sample space are the 52 different cards. So I know it's going to be my bottom number. The first event I am looking at and asking for the probability is, what's the probability that I draw out of that deck the 7 of hearts? Well, right away I know out of 52. Now I got to ask myself, how many cards in the deck are 7 of hearts? Well, there's only one of each card. So I can leave it as a fraction. I think the book might do decimals. It doesn't matter to me. But I'm going to leave it as a fraction because it's easier. Okay, still picking one card. What's the probability that the card I pick is a club card? Well, again, it's out of 52. And if you remember, I told you there are 13 of each suit. So that means there are 13 clubs. Or, that reduces down, 13 goes into 52, 4 times, it's a quarter of the deck, one of the 4 suits. What's the probability that I pick one card out of the deck and it is a face card? Oh, now we got to talk face cards. If you're not familiar with the deck of cards, a face card actually has a face on it, and the cards that have faces are your jacks, your queens, they have a queen face, and then the king faces. So there are 3 cards, but in each of the 4 suits. So there's jack, queen, king of hearts, jack, queen, king of spades, jack, queen, king of diamonds, and Jack, Queen, King of clubs. So altogether there are 3 times 4, 12 cards out of the 52, which reduces down to 3/13. And then the last question, what's the probability that the card I pick is red? So that means I'm still out of 52. Reds are the hearts and diamonds, there's 13 of each, so there's 26 of them, which reduces down to what we could have thought about off the giddy up, is that the red makes up half of the deck, so I got a 50% chance. And then our last set of questions is going back to that family of 3 kids and the gender sequences. So we'll go back to the family of 3 kids. We still need our sample space. If I go grab that set of notes right here. The family of 3 kids, there were a sample space of 8. So all of my probability questions I ask are going to have a denominator of 8, but then I'll have this handy. So my first question, what's the probability that when you have your 3 kids, you have exactly 2 boys? Well, because we took the time to make the tree, this question might be kind of challenging otherwise, but if I look, I want to know how many of these, out of these 8 outcomes, how many have exactly 2 boys? Well, here's 1. Here's another for 2. Here's another for 3. Wrote this one wrong. Let's see, where was they at? 1, 2, 3. 3 of those outcomes. So 3 out of 8 probability. And then our last one, what's the probability of having at least 2 girls? Well, let's think about what that means to have at least 2 girls. So that means I either have exactly 2 girls, or I could have 3 girls, because 3 is at least 2. It's like asking for 2 or more girls. So let's go back and see where I have 2 or more girls. So that would be 1, 2, 3, and 4. So 4 out of 8, or 1/2. Okay, that ends that.